Okay, continuing on with geologic time, the next thing I'm going to talk about is the concept of the formation. Now, there's a branch of geology called stratigraphy, which attempts to organize the rocks into some type of a manageable classification scheme. The basic local unit of stratigraphy is the formation, and a particular rock unit is grouped into a formation based on a distinctive appearance or other characteristics. For example, we can use lithology, rock type, such as grouping sandstones into one formation, shales into another formation. Or we can use other features like color, certain sedimentary structures, and even consider particular depositional patterns in identifying a particular formation. This figure up here, for example, shows some of the formations found in the Grand Canyon, such as the Kebab limestone that occurs at the very top. Notice we also have the Coconino sandstone, the Hermit shale. So these formations are largely distinguished from one another on the basis of rock type. But that's not always the case. In addition to rock type, we can also consider other properties like the texture, the appearance of any organic remains, fossils, the color, thickness, character of the outcrop. It's just whatever is available to the geologist in order to group these different rock types into different formations. In this illustration, to the left, for example, we have three formations distinguished: Formation 1, Formation 2, and Formation 3. In this particular situation, they simply grouped the shales into Formation 1, the limestones into Formation 2, and the sandstones into Formation 3. So that's pretty straightforward. But if we look at the middle sequence, we find that all of the rock units consist entirely of shales. And so we have to use some other factor in distinguishing the formations. And in this case, the geologist grouped the red shale into Formation 1, and the brown shale into Formation 2, and the green shale into Formation 3. So in this case, we're using a color rather than lithology. But then notice the third example to the far right. We have a sequence of interlayered sandstones and shales. But even so, the geologist has been able to distinguish Formation 1 from Formation 2. In this particular example, what was used to distinguish these two different formations? Yeah, we're looking at the outcrop character in specifically what's the difference between Formation 1 and 2. Yeah, notice that in Formation 1, the sandstone layers are thinner than the shale units, whereas in Formation 2, it's just the opposite. The sandstone units are thicker than the formation units. We're looking at C. In C, we can distinguish Formation 1 from Formation 2, even though the entire sequence consists of interlayered sandstones and shales. And the question was, what's the difference between Formation 1 and Formation 2? And you see that Formation 1, the sandstone layers are thinner than the shale units, whereas in Formation 2, it's just the opposite. The sandstone units are thicker. than the shale units. The shale units are distinguished by those horizontal dashed lines, the sandstone units by the stippled pattern. So again, here are the formations of the Grand Canyon, and here the formations are largely distinguished on the basis of lithology. So again, we have the Kebab limestone at the very top, the Coconino sandstone, the, for example, the Bright Angel shale. So it's pretty straightforward in distinguishing these formations, but in other places, the distinction may not be readily apparent. We have to use some other factor. At the very bottom, we have the metamorphic rocks, the Vishnu schist, through which the Colorado River is presently downcutting. The Redwall limestone was probably named simply from the color of the limestone. It's kind of a reddish limestone. Ask me after class. Now let's move on to unconformities. Unconformities represent old erosional surfaces or intervals of missing strata within a rock sequence. And there are three different types of unconformities: angular unconformity, a nonconformity, and finally a disconformity. So let's first of all look at an angular unconformity, which is an old erosional surface separating tilted or folded sedimentary rocks below from flat-lying sedimentary rocks above. The formation of the angular unconformity is shown to the right, where we start out at the very top with deposition of horizontal sedimentary layers within a basin. This is occurring within a seaway, and then maybe sometime later tectonic forces move in, the region is uplifted and folded, and the rocks are eroded down to an erosional surface. And following the formation of the erosional surface, the seas return and deposit additional horizontally layered sediments on top of the old erosional surface. That old erosional surface is therefore an angular unconformity. And notice that it separates sedimentary rocks above from sedimentary rocks below, where the layering tends to occur at different angles, both above and below the unconformity. Here's a famous point in Scotland called Sychar Point, which was visited back in the late 1700s by James Hutton, a well-renowned geologist. But if you look at this rock sequence, notice at the bottom we have vertical sandstones and shales. These sandstones were originally deposited horizontally, but subsequent to that time, tectonic forces came in and flipped or raised or flipped those layers into a vertical orientation. Above the vertical sandstones and shales, we have gently dipping reddish sandstone and conglomerate. And what's separating those two sequences is this angular unconformity, which we can kind of follow by looking at the change between the vertical sandstones below and the gently dipping rocks that occur above. And that marks the old erosional surface. Here we have, if we look at this particular rock layer, notice that it's truncated right at that angular unconformity. It does not extend into the overlying gently dipping rocks. Here's another example. Below we have highly angled sedimentary rocks. Above, the sedimentary rocks are horizontally layered. So we can easily pick out the angular unconformity that old erosional surface occurring at the boundary between those two units. Everybody see this? No, these are sedimentary rocks. Foliation occurs in metamorphic rocks. It's just natural bedding planes due to original deposition of sediments. Now, nonconformity is an old erosional surface separating younger sedimentary rocks above from older igneous or metamorphic rocks below. So notice in this case the nonconformity, that old erosional surface, is represented by this thick wavy line, and below we have both igneous rocks and metamorphic rocks, and that by definition is a nonconformity. Above we have horizontally layered sedimentary rocks like this limestone unit represented by the brick pattern, and above that we have a sandstone unit represented by the stippled, and then finally a shale layer that's color-coded gray occurring at the top. Here we see a sequence of formation of a nonconformity, beginning with metamorphic rock, which has been intruded by igneous rock. And here's our erosional surface at the very top. And over time, the overlying metamorphic rock gets eroded away to a lower erosional surface, in which case the intrusive igneous rock is now exposed on the surface. And then afterwards, the seas come in and deposit horizontally layered sedimentary rocks above that old erosional surface. And so we have here what's termed a nonconformity. So in other words, whenever you get a nonconformity that's underlain by igneous or metamorphic rocks, right away that's a nonconformity. Okay? Finally, we have a disconformity. A disconformity is an old erosional surface where layered sedimentary rocks that occur both above and below are parallel. So in this diagram, this thick wavy line represents the old erosional surface. And notice that we have sedimentary rocks both above and below. And what's more, the layering of the sedimentary rocks are parallel. And that, by definition, is a disconformity. So in the case of disconformities, we start out with deposition of horizontally layered limestone within a shallow sea. And then sometime later, the seas retreat and we get subaerial exposure of the limestones, during which time we get weathering and erosion of that surface. And this is followed by the return of the seas and the deposition of additional limestones directly above that old erosional surface. And so because the limestones above and below are parallel, this, by definition, is a disconformity. Now, here we're looking at the wall, one side of the Grand Canyon, and here's the Colorado River at the very bottom, which is presently cutting through the Vishnu schist. And notice that the Vishnu schist, in turn, is intruded by the Zoroaster granite. And to the right, we have this wavy, heavy red line, which is labeled nonconformity. And the reason it's called a nonconformity is because it's underlain by both igneous and metamorphic rock, and we have layered sedimentary rocks occurring above. Now further up the sequence, at the top of what's known as the Unger group, we have another unconformity represented by this thick wavy line. That unconformity is labeled an angular unconformity. And the reason is because it's overlain and underlain by sedimentary rocks. It's just that the sedimentary rocks occur at different angles. And that angular unconformity is shown in this little photograph towards the left. Does everybody see that?
Oh, yeah.
Okay. And then above that, we have two additional unconformities, both represented by wavy, heavy red lines. These are both labeled disconformities. This lower disconformity occurs between the red wall limestone and the underlying mauve limestone. The second disconformity above occurs between the Supai group and the underlying red wall limestone. Notice in both cases that these disconformities have sedimentary rocks both above and below. And what's more, those sedimentary rocks are parallel. So that fits the definition of a disconformity. Does everybody see this? Any questions on unconformities? So let's move on to the principles of relative dating. In order to relatively date rock sequences, we take into account certain principles. For example, the law of superposition, the principle of original horizontality. We also consider the principle of cross-cutting relationships, in addition to inclusions and unconformities. So I'm going to go through and identify and define each of these different concepts, beginning with the law of superposition. Now, in this particular instance, an undeformed sequence of sedimentary rocks, within an undeformed sequence of sedimentary rocks, according to superposition, each bed is older than the one above and younger than the one below. This was a principle originally defined by a person by the name of Nicholas Steno back in 1669. And it's a relatively simple law. Basically, if you have a sequence of horizontally layered sedimentary rocks, the oldest rocks are going to be the ones that occur at the bottom, and the rocks will then become progressively younger as we move up the sequence, so that the youngest sequence will occur at the very top. In this particular example of the Grand Canyon, within this sequence of rocks, the Supai group occurs at the bottom, so the Supai group is the oldest. And then the rocks become progressively younger going up the sequence, so that the Kebab limestone, in this case, is the youngest of all these rocks. And this simply reflects the original deposition of the sediments, where younger sediments were deposited over older sediments. And this sequence is therefore preserved once the sediments are converted into sedimentary rocks. Now, another important principle is that of original horizontality. Now, this principle states that sediments are initially deposited in horizontal layers, and as a result, the resulting sedimentary rock should also be horizontally layered. On the other hand, if the sedimentary rocks are folded, faulted, or deformed in some manner, then the deformation must have occurred after the original formation of those rocks. So notice that the photograph on the left we see that the sedimentary rocks are horizontally layered. On the other hand, to the right, we see that the sedimentary rocks are highly folded. So if the layers are not horizontal, something must have happened to these rocks after original deposition and lithification to sedimentary rocks. Okay? Everybody see this? So the folding had to have, in this case, the folding had to have occurred after deposition and formation of the original sedimentary rock layers. The principle of lateral continuity states that sedimentary rocks originated as continuous layers that extended in all directions until eventually thinning out at the edge of the sedimentary basin. So if you look at the illustration at the top, we find that all of these different layered sedimentary rocks were once continuous throughout the basin. And along the margins of the basin, we see that the layers end by thinning at the margin of the sedimentary basin. Below that, we see that a large chunk of those original sedimentary rocks have been eroded away, as, for example, occurs today within the Grand Canyon. But we can make the assumption that these rocks were originally continuous. And as a result, we can correlate rocks on one side of the canyon with their counterpart on the opposite side of the canyon. We're assuming that these rocks were originally continuous. And that's basically what that principle states. In the photograph below, notice that the coconino sandstone occurs on both sides of the Grand Canyon, as does the red wall limestone. So this is just one example of lateral continuity. Now, another important principle is cross-cutting relationships. Now, this principle states that if a fault cuts rocks or magma intrudes rock, the fault or the magma have to be younger than the rocks that they cut. In other words, faulting and intrusion occurred after the sediments and sedimentary rocks were initially formed. Here, for an example, in this upper photograph, we see this near vertical fault cutting through the layered sedimentary rocks. As a matter of fact, we see that on both sides of the fault, these rocks have been offset due to differential movement. In this upper photograph, which is the youngest, the sedimentary rocks or the fault? Did the faulting occur before or after deposition of the rocks? Yeah, those rocks had to have been there in order to be offset by the fault, so the fault is younger. In the bottom photograph, we have three things. We have a igneous rock. This looks like granite. And this granite is cut by this dark-colored dike. And then it's also cut by this light, thin quartz vein. So of these three different rock types, which is the oldest? No. So we have here igneous rock, which is cut by this dark vein, or this dike, and then this in turn is cut by this light, thin, white quartz vein. Yeah, the igneous rock has to be the oldest because it's cut by this dark dike. Yeah, the rock itself, this grayish, pinkish gray rock, is the oldest. And this is followed by intrusion of this dark colored dike. And then the youngest is this thin white quartz vein. Notice that the quartz vein cuts both the rock and the dark dike. And so the quartz vein has to be the youngest. Those other two features had to have been there in order to be cut by that dike, by this quartz vein. Yeah, apparently the rock developed a fracture, and late stage magma filled the fracture and crystallized as thin white quartz vein. These are all igneous rocks, which are cross-cutting one another. Here's some other examples of cross-cutting relationships. We have a horizontal sequence of sedimentary rocks which have been cut by faults. Also, the rocks have been cut by dike A. We have a fault B, and even the batholith, which is cutting both fault B and the horizontally layered sedimentary rocks. We'll come back to this block diagram, but these are just various examples of cross-cutting relationships. Now, inclusions are fragments of a rock unit enclosed in another rock unit, and this principle states that the rock unit that supplied the inclusion must be older than the rock that contains the inclusion. For example, we have this sedimentary layer that contains inclusions of both the underlying igneous intrusion and the metamorphic rock through which this igneous intrusion cuts. What's more, the igneous intrusion contains what are called xenoliths, which are inclusions of the adjacent metamorphic rock. So these inclusions are bits and pieces or fragments of older rocks incorporated within younger rocks. This is basically the same figure, and we see that here we have an igneous intrusion, this gray rock, which cuts through adjacent metamorphic rock, which is represented by this wavy pattern. And above these two rocks, we have this old erosional surface, in this case a nonconformity, because it's underlain by both igneous and metamorphic rock. And above that, we have horizontally layered sedimentary rocks. Notice that the lowestmost sedimentary rock contains inclusions of the underlying igneous intrusion. So the question is, which is younger, the sedimentary rock layer or the igneous intrusion? Yeah, the igneous intrusion has to be older than the overlying sedimentary rock, because that sedimentary rock contains inclusions of that igneous intrusion. So the igneous intrusion had to have been there to supply the inclusions to the overlying sedimentary rock. Now notice that the igneous intrusion contains xenoliths, inclusions of the adjacent metamorphic rock. So is the metamorphic rock younger or older than the igneous intrusion? Yeah. The metamorphic rock has to be older than the igneous intrusion in order to supply the inclusions within the igneous intrusion. Well, the idea is that the magma pushed through the metamorphic rock and broke off pieces of it along the wall rock, and those pieces then got incorporated into the magma, but remained solid as solid fragments once the magma completely crystallized into igneous rock. So those inclusions were supplied during intrusion of the magma. On the other hand, the inclusions of the igneous rock within the overlying sedimentary layer, this was an old erosional surface, this nonconformity. It was exposed on the surface, and the intrusion was eroded to provide all these pebbles on the surface. And then the sediment accumulated around these surface pebbles. And when the sediment lithified into a rock, those pebbles were inclusions within the rock. Okay, here we have a block diagram, and all kinds of things are happening. We have tilted sedimentary rock. We have a dike cutting through. We have a sill D, which contains inclusions. We have a unconformity, in this case an angular unconformity, and flat-lying horizontally layered sedimentary rocks above. So let's just go through the sequence of events leading up to this overall situation depicted in the block diagram. So what happened first was that there was an ocean, and beneath the ocean, beds A, B, C, and E were deposited as a sequence of horizontally layered sediments that then lithified into sedimentary rock. Now we know at this point that A has to be oldest, followed by B, C, and then E is the youngest of this sequence. And this is basically just the law of superposition, where younger rocks, horizontally layered rocks, occur over older rocks. So that's stage one. Following the deposition of these and formation of these sedimentary rocks, the next event is that we have uplift and intrusion of sill layer D, which is shown here. Now recall that sills are tabular igneous intrusions that parallel rocks above and below. In other words, and so that fits this type of definition. Now notice that sill D contains inclusions of overlying sedimentary rock E, and the sill also contains inclusions of the underlying sedimentary rock C. And as a result, we know that D has to be younger than both overlying unit E and underlying unit C, because it contains inclusions of both of these rocks. The uplift has caused the C's to retreat and exposing the surface to weathering and erosion. Now the next thing that happens is we get intrusion of dike F. We know that dike F has to be the youngest of all of these rocks formations, because dike F cuts through all of these different units, including sill D. And so in this case, F is the youngest, and this is just simply the principle of cross-cutting relationship. Now following intrusion of dike F, we have a period of erosion, and notice that the upper rocks are eroded away to form this erosional surface. And this in turn is followed by the return of the C's, and at that point we have sedimentary layers deposited on top of that old erosional surface, layers G through K. And so what kind of a, well, it's labeled here, but notice that old erosional surface ends up as an angular unconformity, because for the most part it's overlain and underlain by sedimentary rocks that occur at different angles. Now, that's not entirely true, because this unconformity where it crosses the underlying sill, that's actually a nonconformity. But in all other places, E, C, B, A, that's an angular unconformity. And following the retreat of the seas, we end up with this modern erosional surface, and that pretty much completes our block diagram. We've reconstructed the geologic history of this area using the principles of various principles. Now, this is all relative dating because we do not know the actual ages of any of these events. For example, we do not know the age of the dike. We do not know the ages of these sedimentary layers or the unconformity. All we've done is put all of these different events in their order of occurrence. And that's basically what relative dating is. Any questions? So here's another example. Let's go through and place each of these different rock units and features in order of occurrence. And I'll start us off by beginning with the deposition of the limestone, the sandstone, and these other horizontally layered sedimentary rocks up to the base of the conglomerate. Now, why do we stop at the conglomerate? Why don't we include the overlying conglomerate and shale at this point? Yeah, we have a fault A that cuts through, but notice that it stops below the conglomerate. In other words, fault A is truncated by the conglomerate. And as a result, the conglomerate likely was not there at the time of faulting. So what's the next? So the next event to occur was the faulting A, because fault A cuts the limestone and the sandstone. Now, following fault A, what's the next event to occur? Pardon? Yeah. That's followed by the deposition of the conglomerate and the shale and the other rock units. Now, to determine what follows afterwards, if you look to the right of the block diagram, here we have a fault B, we have a dike B, and we have a batholith. Now, considering fault B, dike B, and the batholith, what is the next event to occur of those three? Be careful, we have cross-cutting relations. Yeah, notice that dike B cuts fault B, and so does the batholith.
Wait, but does dike A cut fault B? Little dot dike A
Yeah, let's ignore dike A right now. Let's just focus on fault B, dike B, and the batholith. Of those three, which is the oldest? Yes. Notice that dike B and the batholith both cut fault B, and so those two features have to be younger. Now, between dike B and the batholith, which is older? yeah, the dike B cuts the batholith, so that following fault B, we have the emplacement of the batholith. And then after the batholith is in place, this is followed by emplacement of dike B. And notice that dike B reaches only the base of the conglomerate and then spreads out as a sill. On the other hand, dike A cuts that sill. And so which is younger, dike A or dike B? Yes. Dike A has to be younger than dike B because it cuts the sill. So dike A is the youngest feature. This is relative dating. Again, we use these different principles to reconstruct the order of occurrence without actually assigning ages. Any questions? So actually, what's happened? The most recent event is simply the present erosional surface, and eventually, once this erosional surface gets covered by additional sedimentary rocks, it'll become a nonconformity. Now, next time we're going to see how we can actually assign ages to these different events, and that'll be the topic of radiometric dating. But anyway, we're finished for today.